Okay, this video is about a worksheet that I'm giving to my students in class related to position, velocity, and acceleration of a particle. So particle motion, right? Position is your original x function. Let's move this around. So this is x sub t, right? Your position function. The velocity is the derivative. So velocity is the derivative of your position function. And then acceleration is the second derivative of your position function. Okay, so position goes to velocity, velocity goes to acceleration. So we just take derivatives more and more if you want to get to something else. Okay, but this isn't really about that. Here we have graphs, right? So here I have graphs. So here's figure 1 about a bug crawling. This is a velocity graph, right? The velocity is given by this. Okay, this one is also a velocity graph. Okay, and then this third one is a table of, well, velocities. Okay, so none of these talk about position. These are all velocities, which is good, right? Velocity is the, right, positive and negative, so we can tell when it's moving right and when it's moving left. So if the velocity is positive, right, above the x-axis, your particle is moving to the right, and if your velocity is negative, below the x-axis, then your particle is moving to the left. Okay, we can also get the acceleration by simply looking at the slope of your line. Okay, so acceleration is the slope or the derivative of velocity. Okay, same thing up here. The slope is the derivative. So acceleration is the slope of your lines because our lines are velocity graphs. So let's see if we can explain what's going on with some of these here. Okay, this one, number 1. We're simply asked to find the slope of the tangent line, so we just have to find y prime. In other words, take the derivative of this function and then plug in 0. Okay, so that one hopefully is not a mathematically challenging problem for you. Okay, number 2. At what time does the particle move to the right? Okay, begin to move to the right. So we're looking for when is the velocity initially going to be positive. So look on your graph and see when the velocity is going to be above the x-axis, right? And then that is the time, this time, the first time when the particle moves to the right. Velocity is above the x-axis. Okay, find the derivative of the function. So this is, once again, a quotient rule because it's a fraction. Quotient rule, low d high minus high d low over low low. Okay, and then plug in 0 and get your answer. Okay, find the first point on the graph when the particle speed is increasing. So speed is increasing when your velocity and your acceleration have the same sign. Okay, so they can both be positive or they can both be negative. Okay, so it doesn't matter in which direction we're going. We want to know when the speed is increasing. So they can both be negative, right? If velocity and acceleration are both negative, okay, acceleration is negative. This is acceleration in the left direction, right? Because when velocity is less than 0, it's going left. And if your velocity and your acceleration are both positive, that is acceleration to the right. Okay, speeding up to the right distance, or in the right direction rather. Okay, so if velocity is positive, then we're speeding up to the right, and if velocity is negative, we are speeding up to the left. And of course, if they're opposites, then you are slowing down, right? Your speed is decreasing to the left, or your speed is decreasing to the right. So find the first point when you have the same sign, when the slope and the velocity are both positive or are both negative. Okay, the bottom one, find the slope of the tangent line. Once again, this is just looking for y prime. So this is a product rule. So this is f times g, where all of this is going to be your g. Okay, now we might have some trouble finding the derivative of 1 over x cubed. So hopefully that won't be a problem. Let's look at 1 over x cubed by itself. So if this is our function, then the derivative we can write the function again as x to the negative third power. Okay, that's sometimes handy to do when it's just a single x in a denominator, because then x prime becomes negative 3 times x to the negative fourth. And then we can put this back in the denominator to have one simple fraction, negative x cubed over x to the fourth. Okay, so that's how you're going to find the derivative of 1 over x cubed once you do your product rule, right? So the product rule is f prime times g plus f times g prime, right? No dx dt's. We're not taking with the respect to time. This is simply a derivative problem. Okay, let's come up now. We're at the bottom. Find the derivative. So once again, this is just finding y prime. Okay, so nothing tricky. Well, maybe something tricky, right? So we can do 1 over root x, and we can use the quotient rule if we want to, right? Low d high times high minus high d low and stuff. As long as you remember what the derivative of root x is. Okay, remember the derivative of root x is going to be 1 over 2 root x. So when we take that derivative here, we get 1 over 2 root x. Okay, all over low, which is root x quantity squared. Okay, and then do some simplifying and then plug in x. Actually, we don't even have to simplify. Just plug in x equals 1 and see what you get. Okay, so if it's just a plug and chug, you don't have to simplify that problem there. Okay, find the slope of the tangent line. So this is simply, once again, taking the derivative and plugging in 1. Okay, take the derivative whenever it says slope. Find the second point on the graph where the particle speed increases in the positive direction. So positive direction, remember, is velocity is positive. It's above the x-axis, right? So velocity is positive when the graph is above the x-axis. So we want to know when is the graph above the x-axis and when acceleration is positive. So we want the slope of the line to be positive and it to be above the x-axis, okay? And the second point when that happens. Apparently it happens twice. What is the acceleration on this interval? Okay, so we need to know, when it's talking about acceleration on an interval, they want average acceleration. Okay, and to find average acceleration, we do the velocity at time 7 minus the velocity at times 4. Okay, so this is a slope formula, right? Velocity at 7 minus velocity at 4 over 7 minus 4. So we're getting the y values, right? This is going to be a y value from your graph, and this is a y value from your graph also. Okay, acceleration on an interval is a slope problem. Okay, a particle moves along the x-axis given by this function. Okay, find the displacement during the first 2 seconds. So displacement is the same as net distance traveled. Okay, net distance. So to find the displacement, we're going to take the position at times 2 and minus the position at times 0. Okay, now let's see. Displacement is not absolute value. So we just want to know, where is the particle, how far is the particle from its original position after 2 seconds. So x of 2 minus x of 0. Okay, so there we go. Remember, no technology is allowed, so don't be taking derivatives or anything. All these numbers are nice and pretty. Okay, and from the back side, find the average acceleration from the rocket over time t equals 0 to 80. So remember, average acceleration is the velocity at time 80 minus the velocity at time 0 over 80 minus 0, right? Average acceleration. So over the whole entire thing, what's its average? Okay, refer to figure 1. At what time does the bug begin to move at a constant rate? So constant rate means velocity or acceleration is 0, right? We are not accelerating at all. So this is going to talk about when is the velocity have a horizontal line, right? Because a horizontal line has a slope of 0. So we're looking for the velocity. When is the acceleration 0? Is the velocity is constant. Okay, a horizontal line. What is the average velocity? If this is the position, then average velocity is the position. So x of 3 minus x of 0 over 3 minus 0. And in this case, you get your value by plugging in 3 and 0 into your function. Okay, into your function, right? We don't have a graph, so we have a function. X of 3 minus x of 0 divided by 3 minus 0. Average velocity is a slope problem, so we make a slope equation. Okay, at what value does the particle change direction? Okay, so what we need to do is, that means the velocity is 0. So we have to take the derivative of our position function, right? The derivative of this, figure out when that's 0. Okay, so maybe that's 0 here at t. And then we have to do a sign analysis, right? Maybe it's positive on the left and negative on the right. So it has to change signs in order to change directions. If it's positive and positive, then it might come to a stop here, but it doesn't change direction. It continues going in the same way. So we have to figure out when is your t equal to 0, right? So we take the derivative. When is our velocity 0? Take the derivative of our position function, set it equal to 0, and solve. Okay, and then we do a sign analysis to see if our signs change from left to right, or if our signs stay the same. Okay, so there's a little bit to do with these kind of problems. When it comes to changing direction, you have to show that there is a change of sign in order to have a change of direction. Okay, let's see. So this is a position, right? The height in feet, so that's the position, is given by this function. I'm sure that this is some type of a negative quadratic, so maybe it goes like that. Who knows? And we want to know what is the velocity of the flare when it's moving towards the ground. Okay, so towards the ground is on this half of our graph, right? The right side is when it's moving towards the ground. When its position is 131 feet, so maybe this is 131. Okay, so this is your time when it's going up, so we want to figure out what is this time right here. Right, what is the time when it's coming down? Velocity is the derivative of your position function. So we take the derivative of this. Okay, we figure out what this time is. When is that thing at 131 feet? When? So we have to put equal 131 and solve for that equation, right, to solve for time. So you set 131 equal to negative 3t squared plus 100t plus 3. Okay, you could use, actually this is probably a factorable quadratic. So we're going to make this into a quadratic equation. 3t squared minus 100t plus 128 equals 0. Right, when you bring that over. So hopefully this is factorable. 3t and t. They're both going to be negative, right? They're both got to be negative. So we just need to figure out what the factors of 128 are that give us 100 when we add them together. Okay, and then we're going to take the one on the right. So it looks like this one will be the one on the right, the time. And plug that into your derivative function to see what the velocity is. Okay, let's see. A particle moves along the x-axis. What is the instantaneous velocity? So this is the derivative, right? Instantaneous velocity means derivative. So we want to find x prime at 3. And I'm sure you are plenty capable of finding the derivative of that and plugging in 3. Find the estimated for acceleration at 35 seconds. So figure 3 doesn't have 35 seconds as an option, but it does have 30 and 40. So the average acceleration, or the estimate or approximate acceleration, is once again the velocity at 40 minus the velocity at 35 divided by 4. So not 35, 30, right? We have a velocity of 30. So v of 40 minus v of 30 over 40 minus 30, right? This is your average or your approximate acceleration, the slope of your velocity. Okay, so we take those two times around 35 and we figure out what that fraction is. And number 1, at what time, what value of t does the bug change direction? So once again, that's looking for when is it positive to negative, right? So if it's negative on the left and positive on the right, it changes directions from left to right. And if your bug is this way, if it's positive to negative, then it changes from the right side to the left side. Okay, so hopefully this circuit isn't very hard, and you don't need to actually watch this video to be able to understand it. Okay, maybe this derivative down here on maybe this one, right? These ones might be kind of hard to derive once in a while. And maybe this one down here, the Matt Damon flare one, the Martian. I think everything else you've done a pretty good job of. Okay, so position, velocity is the derivative of position, and acceleration is the derivative of velocity.